Hi friends, welcome back to Edupedia world. Today we'll continue our discussion on electromagnetic induction and we will specifically see an example where electromagnetic induction is put to use, namely AC generator. We will see the construction of AC generator, the working of AC generator and what exactly does it do. Then to close the chapter, we will see the comparison between DC current and AC current, also the comparison between AC generator and a DC motor. So let's start with AC generators. Today's lecture we will discuss about the first practical application of electromagnetic induction. We'll see how a AC generator works, but before that let's see what a AC generator is. An AC generator is basically a device which converts mechanical energy into electrical energy, and it uses electromagnetic induction in order to do this. With this background, let us see the construction of an AC generator. An AC generator has a magnet arranged like this. The north pole is here, the south pole is here, such that magnetic field is from the north pole to the south pole. Okay, then we have a copper coil, insulated coil, and inside this here is soft iron core, and there are number of turns in the coil which is wrapping the soft iron core, and these are attached to what is known as the slip rings. This is a slip ring. One of the end of the copper wire is attached to this slip ring over here, and the other end of the copper wire is attached here. Now this slip ring is connected with a carbon brush, and that gives connection to the load. This is the load that will consume the power that is being generated. Okay, and this brush connects to the other terminal of the load, thereby completing the circuit. Now this whole coil system is manually rotated. This is the mechanical energy we provide to rotate the coil. This is the basic structure of a AC generator. Now let us see how exactly the AC generator is working. To begin with, I have drawn the north pole here and the south pole here, and these are intermediate steps of the coil position. We are starting with the coil being perpendicular to the magnetic field. So basically the plane of the coil is perpendicular to this direction. What does that mean? That means maximum amount of magnetic field is passing through the cross section, isn't it? Since the whole area is exposed to the magnetic field, which is in this direction, maximum amount of magnetic field is able to travel through the coil. Let's assume this is our initial location, initial position, that is 0 degree. Now mechanically what we are doing, we are rotating it, let's say clockwise, seeing from this direction. So we are moving it in this direction. As the coil starts moving in this direction, what is happening is that the amount of magnetic flux passing through the coil is starting to reduce. And as we know from electromagnetic induction theory, that any change in magnetic flux leads to electromagnetic induction EMF being induced, right? So as soon as the coil starts to rotate, the electromagnetic force starts to increase. Initially it was 0. As the coil starts rotating, the electromagnetic field EMF starts to increase. it reaches a peak at 90 degree. What is the 90-degree location? The 90-degree location is when the plane of the coil is parallel to the direction of the magnetic field. And under this circumstance, what is happening, that zero magnetic flux is passing through the coil. Therefore, the chances for the change of magnetic flux is the maximum at this location, right? Because if you rotate the coil by even a little degree, a lot of increase in magnetic field or magnetic flux will take place. Therefore, this location is location of maximum electromotive force, which means that the rate of magnetic flux change will be maximum when the plane of the coil is parallel to the magnetic field. Now what we are doing is we are further rotating it. On further rotating it, the magnetic field, change of magnetic field, the rate of change of magnetic field will keep on decreasing. It will keep on decreasing until it reaches 180 degree. And at 180 degree, what will happen? Again, a situation like this happens, but the only change is that we have just revolved the whole system by 180 degree. Again, maximum magnetic field is passing through the cross section, right? Therefore, at this location, if we change very slight, we rotate it very slightly, there will be negligible change in the magnetic flux. Therefore, this is again the location of zero EMF. Now we start to rotate it further from 180 degree, and now what will happen, since the direction of this has changed, initially it was here and now it is here, any further rotation will lead to increase in EMF but of opposite sense. So if this was positive EMF, here we will have negative EMF. In other words, what this means is that the direction of current will reverse. So if here the current was passing in this direction through the load, beyond the 180 degrees, what will happen is the current will pass in this direction through the load. So the direction of movement of current has changed. And from 180 degree to 270 degree, again the amount of EMF generated keeps on increasing slowly till it reaches a situation where the plane of the coil is parallel to the magnetic field. Beyond that, from 270 to 360 degree, again the magnetic field magnitude will starts to reduce, though it is in the opposite direction, negative sense, but if we see the magnitude, it starts to reduce, and finally at 360 degree, which is equivalent to the 0 degree situation, we are back to zero EMF, right? And again the whole cycle repeats. So we go from 0 minimum EMF to 90 maximum EMF to 180 zero EMF to 270 maximum EMF in the opposite direction to 360 or 0 degree, again at 0 EMF. This is how the AC generator works. Okay, and what we are seeing here is that the polarity of current, that is the direction of current, changes each cycle. Half of the cycle it is positive, half of the cycle it is negative. Therefore, in an AC current setting, the direction of current flow is continuously changing. Now, if we want to decide what is the frequency of the AC current, the frequency of AC current will be same as the frequency of rotation. Okay, so each time one complete rotation takes place, the EMF change also completes one rotation. So these both are parallel concepts. Okay, now let us see what is the EMF induced. Suppose there are n rotations in per second, that is the whole system is rotating n times per second, then we can estimate the EMF as E0 sine of 2 pi n t, where n is the number of revolutions per second. E naught is the maximum EMF, that is this value. Okay. Similarly, the current flowing I can be written as I naught sine 2 pi n t. Current will also be having the same frequency as the EMF. Okay, and as we said that this E naught and this I naught are the maximum EMF generated and the maximum current flowing through the circuit. This should give you insight into what a AC generator is and how does it work. You need not know this, but just for sake of completion, E naught is basically equal to 2 pi n b n a, where n is number of revolutions per second, b is the magnetic field, capital N is the number of turns in the coil, and a is the area of cross section. So seeing this, what we can say is that we can increase the EMF either by increasing the number of revolutions per second, or by increasing the magnetic field, increasing the number of turns in the coil, or by increasing the area of cross section of the coil. Fine. One important thing to note is that the electric supply that we receive is normally at 50 Hz. The frequency of the electric supply we receive is 50 Hz. Okay. Now, what is the basic difference between AC current and DC current? AC current, also known as alternating current, is current in which the direction of the sense of EMF is continuously changing. Also, the magnitude of EMF is continuously changing. DC current, the direction of EMF remains constant. Also, the magnitude remains constant. So, DC current or direct current do not have any frequency. It remains in the same direction throughout. Okay. Now, what are the advantages of AC over DC? AC's advantages over DC are that you can tailor the amount of voltage. You can increase or decrease the amount of voltage in an AC system by using what is known as a transformer. You cannot really do that in case of a DC settings. Also, when electricity is transmitted through long distances, as we discussed, this stepping up of the voltage leads to reduction in the electrical losses. That is why AC current is used for household purposes, as it facilitates large distance travel for the generated current from the power station to the end consumer. Okay, one last note. The comparison between AC generator and a DC motor. AC generator is basically converting mechanical energy to electrical energy, whereas DC motor is doing just the opposite thing, that is converting electrical energy to mechanical energy. Okay, AC generator works on the principle of electromagnetic induction. DC motor works on the principle of Lorentz force. The Lorentz force created actually leads to the movement. Okay, and one thing is that in AC generator you need to move this manually, thereby providing the mechanical energy. In DC generator, the movement is the result of the current you are applying. So this discussion should give you a good idea about the utility of electromagnetic induction and how this is used in practical scenario to actually generate current just by using a magnet and a source of mechanical energy. Next class we will see another application of electromagnetic induction, that is known as transformers. We will discuss that in length. So till the next class, have a great day. Goodbye.